Good day. So we are going to have our next topic, which is uniform circular motion. Let us have the definition of terms. So an object in a circular path is accelerating, whether or not its speed is constant. So for example, you have an object that is moving around at 50 kilometers per hour on a circular path. No? Um, Even though the magnitude is constant at 50 kilometers per hour, there can be acceleration because the direction of the object is constantly changing. Okay, the reason is given here. This is because there is a continuous change in the direction. The acceleration is centripetal because it is directed toward the center of the circular path. Okay, so paloob siya. One type of motion on a circular path is uniform circular motion. Okay, these definitions are taken from page 63 of your book, okay, Exploring Life Through Science. Okay. What is centripetal force? Okay, force producing centripetal acceleration is centripetal force. The magnitude of the centripetal force varies directly as the square of the velocity of the body and inversely with the radius of the circular path. Okay, so from the previous slide, we know that A sub c, the centripetal acceleration, is given by this equation. A sub c equals v squared over r. Now, um, for the centripetal force, now going using Newton's second law, F is equal to m times A, we substitute the equation for uniform circular motion, okay, such that you have F is equal to m v squared over r. That's how you have this statement. The magnitude of the centripetal force, the F sub c, okay, varies directly as the square of the velocity. So the velocity is squared and inversely with the radius, okay, of the circular path. So here in this figure, the radius is given by this one. It's the length from here to this point. Okay, in this figure, the radius is from here to here. In this figure, from here to here. And in this figure, from here to here. And in this figure, from here to here. Those are the radii. Okay, it's directed towards the center and it acts on the rotating mass. In the examples that we have, the rotating mass here would be this, okay, the ball here, the car, okay, you have here the cart, and you have here the earth. Okay, these are the rotating mass. Okay, ito yung kailangan natin i-substitute yung mass dito. Okay, let's go to the next. Centrifugal force, reaction force to the centripetal force. Okay, so if you have forces moving inward, there should be force that counters the centripetal force. We call that the centrifugal force. It is equal in magnitude but opposite in direction. In which direction? It's outward. Okay, exerted by the rotating body upon the agent. That applies the centripetal force. So this is exerted by the object. Okay. Now, let us go back to the equations for centripetal acceleration. There are three mathematical quantities that will be of primary interest to us as we analyze the motion of objects in circles. These three quantities are speed, acceleration, and force. Okay, so the speed of an object moving in a circle is given by the following equation. So this is the speed now. We know that speed is distance divided by time. So r is equal to d over t. But in a circular path, okay, the circumference is given by 2 pi r, r meaning the radius. Okay, and time we represent it with a capital letter T. Okay, it represents the period and r represents the radius. Okay, the acceleration of an object moving in a circle can be determined by either two of the following equations. So a is equal to v squared over r. Since we have v as 2 pi r over t, we substitute it into v squared. Okay, upon substitution, you will get this equation for pi squared r over t squared. Please take note of the definition of capital R and capital T here. Okay, so the one that we're using a while back is the small letter r. Okay, so we distinct those two are the same. It's just that we're using a different textbook from where I got this equation. Okay, kaya nilagay niya capital R. The same is true for time. Okay, let's go to the next. Okay, equations for force in uniform circular motion. We have this derived two slides back. Okay, so the F net from the second law of motion is F equals m times a. And instead of writing a, we substitute the one for uniform circular motion, okay, centripetal acceleration. So you have v squared over r. Now, from this equation, there is another form for v. Okay, so we substitute the values that we have here, 2 pi r. Okay, that's what we got here. Okay, so you have another equation, m 4 pi squared r over t squared. The equation in the middle and on the right are derived from the equation on the left, okay, this one, by the substitution of the expressions for acceleration. Okay, so with those equations, let's go to some sample problems. Okay, number one, a Ferris wheel has a diameter of 3.0 meters and rotates at a speed of 2.0 meters per second. So we're given the diameter, the capital letter D, 3.0 meters. Now we know that the R is 1.5 meters. We divide the diameter by 2, okay? And rotates at a speed of 2.0 meters per second. Find the net force acting on a 35-kilogram child riding in one of those on the cars of the Ferris wheel. So ito yung Ferris wheel. Okay, umiikot siya, no? And there's a cart here. Let's assume that, that this one is the child. The mass of the child is 35.0 kilograms. So we are asked about the net force acting on a 35-kilogram child. So F in this case is a centripetal force. This would be mv squared over r. Now the units for centripetal force, okay, will be the same as that for ordinary forces. It will be in newtons. Okay, so the mass is 35.0 kilograms. The V is 2.0 meters per second. Then we square it. And then the radius is 3.0 meters. Let us check if all the units are in MKS. So mass is in kilograms. The velocity is in meters per second. And the radius is in meters. So you will get newtons here. Okay, so let's use your calculator. 35 times 2 squared divided by 3, you get 46.66 newtons. Okay, so we round this off to two significant figures. You get 47 newtons. That would be the net force acting on the 35 kilogram child. Okay, let's go to the next. The centripetal force acting on a 35 kilogram boy is 125 newtons. So this time around, you are given the centripetal force when he is standing on a merry-go-round having a speed of 2.0 meters per second. Okay, this time, how far from the axis of rotation is the boy standing? So we're looking for the R. Okay, so the the equation that we will be using is F equals mv squared over R. Okay, in this case, the given is F, the given is M, and the given is V. So we transform the equation. So you get mv squared over F. Okay, the mass of the boy is 35.0 kilograms. The velocity of the merry-go-round is 2.0 meters per second. Then don't forget to square this. And the F is 125 newtons. Okay, so let us compute for the R, or the axis of rotation. So 35 times 2 squared divided by 125, we get 1.12 meters. Okay, so we express our answers into SF, 1.1 meter. Okay, so let's go to the next problem. Number 3, an Indy car with a speed of 120 kilometers per hour goes around a level circular path track with a radius of 1.00 kilometers. What is the centripetal acceleration of the car? Okay, so um, centripetal acceleration A sub c is equal to v squared over r. Okay, so since we are looking for centripetal acceleration, we want it to be expressed in MKS form, so meters per second. No, we need to convert 120 kilometers per hour. Let's express this in meters per second by our shortcut, which is divide this by 3.6. Okay, so 120 kilometers per hour is equivalent to 33.33 meters per second. And for the radius, we convert this, okay, to meters. You get 1,000 meters. Okay, so we substitute this into the equation, 33.33 squared divided by the radius 1,000 meters. So what do we get? So 33.33 squared divided by 1,000, you get 1.111 meters per second squared. Okay, so we use 2SF, you get 1.1 meters per second squared. So this is the centripetal acceleration of the car, 1.1 meters per second squared, directed towards the center. So if you were asked to illustrate this, okay, you have the circular path. This is the car. The acceleration is headed towards the center. This is A sub c. Okay, let's go to the next problem, number 4. A car of mass 1.5 times 10 raised to the third kilogram rounds a circular turn of radius 20 meters. If the road is flat and the coefficient of friction is zero point 0.5 between the tires and the road, how fast can the travel uh, how fast can the car travel without skidding? Okay, so we need to illustrate this. Okay, so this is our car and the mass is given 1.5 times 10 raised to the third kilograms. Okay, the road is flat and the coefficient of friction that is static would be 0.50 between the tires and the road. So we are asked find V. Okay, so there is what we call centripetal um, force provided by this mass, and that is equivalent to mv squared over r. Okay, so if this mv squared over r is heading towards the center, then there should be an opposite force, and that is provided by the frictional force, Ff. Okay, so these are the two forces that counter each other so that the car remains in this circle. So it does not go out of the circle or it does not go into the circle. So they should cancel out. So in effect, we have the summation of Fx is equal to 0. And we think of the forces. Okay, the summation of forces here, this being along the x-axis, what are the forces acting on the object? Okay, so you have negative FCP, the centripetal force, plus the positive FF is equal to 0. Okay, so FF being the frictional force. So the frictional force we have studied last time, the frictional force is mu Fn. And mu is provided in this problem. It's zero point 0.5. And what is Fn? Fn is the weight of the car. How do we get the weight of the car? From here. Okay, so 1.5 exp3, we convert that to newtons. That would be 14,700 newtons. Okay, so times 9.8. Okay, so we substitute the equations you have for CP. So the next step here, the CP is negative m v squared over r plus mu f sub n equal to 0. Okay, so we would like to solve for v. this one. Okay, so um, move this to the other side. You have mv squared over r equals mu f n. Okay, that would be our working equation. Let me just change the color to black. Okay, so computing for, sorry, computing for v is equal to, you have mu Fn times r divided by mass, then square root everything. Okay, so this is equal to, the mu is zero point 0.5, the Fn is 14,700 newtons, oops, and the radius, is it given, 20 meters, divided by the mass, 1.5 times 10 raised to the third kilograms. Okay, we are given the mass. Using your calculators, get the square root of zero point 0.5 times 14,700 times 20. Okay, divide everything by 1.5 exp3. What do we get? You get 9.89 newtons. Okay, so sorry, not newtons. That's the speed will be 9.89 meters per second. And then we round this off to 1 SF, so 10 meters per second. This would be our answer for number 4. Okay, let's go to number 5. Number 5, a 900 kilogram car moving at 10 meters per second takes a turn around the circle with a radius of 25 meters. Determine the acceleration and the net force acting upon the car. Okay, so F is equal to mv squared over r to get the force. But for the acceleration, it would be v squared over r. Okay, so the v is 10 meters per second, then we square it. The radius is 25.0 meters. So this would give us 10 squared divided by 25. So the centripetal acceleration is 4 meters per second squared. Okay. Then we substitute into this equation. F is equal to, um, sorry, this is the wrong equation. Wait. It should be mv squared over r. Let me erase this. Okay, this is m v squared over r. Okay, so we have already solved for v squared over r. It's 4 meters per second squared. The mass is 900 kilogram. Multiply this by 4 meters per second squared. You get 3,600 newtons. Okay, and we follow the rules on significant digits. Dapat 1 SF, so 4,000 newtons. Okay, let's go to the last problem. Okay, the last problem is that the equation that we will be using here is the law of universal gravitation, yung G. So remember, you are asked to compute for the G in Jupiter. So to compute for the G in Jupiter, you have small letter g is equal to g m, the mass of Jupiter, divided by the radius, okay, the mean orbital radius, how far, and then ito naka-squared, okay? So the g is 6.67 times 10 raised to negative 11. The unit is Newton meter squared per kilogram squared. Okay, the mass of Jupiter is given as 1.89 times 10 raised to the 27 kilogram. Okay, divided by, okay, the radius, this one should be converted to meters. So 778 million. Okay, but don't forget to convert this. Okay, so times 10 raised to the third. Okay, times 10 raised to the third meter. Then, naka-square siya. Okay, so let us find the small letter g of Jupiter. So 6.67 exp negative 11 times 1.89 exp 27 divided by 778 million exp3, then dapat naka-square siya. This will give us 2.08. Napakaliit. Wait, 6.67 exp negative 11 times 1.89 exp 27, 17. So divided by 778, oops, exp3. Okay, sobrang liit ng answer. exp negative 11 times 1.89 exp 27. Okay, so the answer that you will get is 2.083 times 10 raised to negative 7 meters per second squared based on what we have here. Okay, thank you very much.